Massive stone blocks crossed entire countries without a single wheel. Ancient engineers achieved the impossible with nothing but wood, rope, and sheer intellect. This is the story of how ancient engineers moved mountains without iron or wheels, and by the end, you will understand the brilliant, sustainable principles that let them reshape the world. We will uncover how they floated stones heavier than elephants and made entire statues walk for miles. What forgotten innovation from the past most surprises you? The true genius of these ancient builders is found not in what they lacked, but in what they chose to use. Their toolkit was forged from the earth itself, a sophisticated array of natural materials, each selected for a precise purpose. Stone hammers were not just any rock, they were crafted from dolerite, a stone harder than granite, capable of shaping the very blocks of the pyramids. Levers were not simple logs, but hewn from resilient hardwoods that could bear unimaginable weight without splintering. And the ropes that pulled these masses were not crude vines, but meticulously braided cords from plant fibers like hemp or papyrus, possessing a tensile strength that could rival some modern synthetic lines. Consider the challenge of cutting granite, one of the hardest stones on earth, with tools softer than the material itself. Egyptian artisans achieved this with copper chisels. Copper is a relatively soft metal, so how did they manage it? The secret was an ingenious use of simple abrasives. They would score a line on the granite surface with the copper chisel, then pour a slurry of wet sand into the groove. The sand, rich in quartz particles harder than the granite, did the actual cutting as workers sawed back and forth. The copper tool was merely a vehicle for delivering the true cutting force, the relentless grind of sand and water. This was not a crude bashing of rock against rock. It was a refined process of material science, understanding that the combination of a soft metal and a hard abrasive could overcome a seemingly impossible barrier. This profound resourcefulness defined their entire approach. The limitations of their available materials did not hinder them. It forced a wave of incredible creativity. They could not invent a steel cable, so they perfected the art of rope making, twisting plant fibers into cables thick enough to haul a 100-ton obelisk. They had no hydraulic cranes, so they mastered the physics of the wooden lever and the rolling log, understanding that friction could be managed and weight could be redirected. Every tool was an extension of a deep, intuitive knowledge of the natural world. This intimate relationship with their primordial toolkit is what set the stage for the monumental tasks to come, proving that the greatest engineering begins not with the most advanced technology, but with the most profound understanding of what is already at hand. With their simple but effective toolkit, ancient engineers unlocked the power of fundamental physics. The principle of leverage was their silent partner in every impossible lift. A long wooden beam, when placed over a sturdy fulcrum of stone or wood, became a machine of immense power. The secret was in the distances. By applying force to the very long end of the lever, the short end, tucked under a massive stone block, would exert a force many times greater. A small team of workers, pushing down rhythmically, could lift a weight that would otherwise require hundreds of people, all with a level of control that allowed for precise placement of stones weighing tons. This same logic of trading distance for force was applied on a grand scale with the inclined plane. Instead of lifting a block straight up, they would build a great ramp of earth, mud, brick, or stone, creating a long, gentle slope to the desired height. Pulling a heavy object up such a ramp required far less effort at any given moment than a direct vertical lift. The steeper the ramp, the harder the pull, So ancient builders constructed these roadways with a very shallow incline, sometimes stretching for nearly a mile. At the site of the Great Pyramid, evidence points to the use of enormous ramps, possibly spiraling around the rising structure itself, allowing workers to drag blocks all the way to the summit. Think of pushing a heavy cart up a hill. A gentle slope is always easier than a steep cliff. They were not fighting the weight head-on, they were outsmarting it, coaxing it upward one manageable step at a time. This deep, intuitive grasp of mechanics, using leverage and slopes to make the impossible merely difficult, set the stage for even more creative solutions when the terrain itself became the obstacle. But this mastery of solid mechanics was only half the story. Ancient innovators also learned to command the fluid power of water, transforming rivers and canals into their most powerful labor-saving devices. Water became more than just a resource for life. It was a dynamic tool for moving mountains. In mining operations, engineers would channel water to erode entire hillsides of soft rock, washing away the earth to reveal valuable ores beneath. This hydraulic mining was far more efficient than digging by hand, using nature's own force to do the heavy lifting. For transporting the resulting stone or timber, they turned to the waterways themselves. They would float massive logs downstream or lash stones to rafts, letting the current carry a weight that would have taken thousands of men to drag overland. The river did the work, and the engineers simply guided the process. There are even compelling theories that they used water in more subtle ways to move individual blocks. By creating carefully leveled and contained channels, they could slide enormous stones along a path made slick with wet clay or mud. This liquid lubricant would dramatically reduce the ground friction, turning a near-impossible drag into a manageable push, a clever trick of hydrodynamics long before the term was ever invented. The ancient Chinese, for instance, were masters of this, employing complex canal systems and water-powered machinery in their massive construction projects. They understood that water's relentless, flowing force could be harnessed to achieve what human or animal strength alone could never accomplish. This was an early, brilliant form of eco-engineering, a philosophy of working in concert with the environment's inherent power rather than struggling against it. They did not seek to conquer nature but to collaborate with it, and in doing so, they unlocked a source of energy that was both limitless and free. This silent battle against friction was where ancient ingenuity truly shone. The greatest force they had to overcome was not the sheer weight of the stones, but the stubborn grip of the ground itself. To move a multi-ton block, you must first defeat the immense friction holding it in place. Ancient engineers became masters of this subtle art, developing solutions that were both elegantly simple and devastatingly effective. One of their most brilliant tricks was to turn the earth against itself. In Egyptian quarries, murals and practical evidence suggest they did not simply drag heavy sledges across dry sand. Instead, workers would walk ahead of the colossal load, pouring water directly onto the path. The dampened sand, or the clay beneath it, underwent a remarkable transformation. The water particles reduced the internal friction between the sand grains, creating a hard, slick surface. What was once a granular, gripping terrain became a smooth, slippery mud path, dramatically lowering the coefficient of friction. A sledge that would have required the strength of hundreds to budge could now be pulled by a much smaller team, gliding forward with surprising ease. This was not magic, it was an early, practical application of tribology, the science of interacting surfaces. They observed that a wet path was a smooth path, and they applied that observation on a monumental scale. Another widespread innovation was the use of logs as rollers. This was not a simple, static platform. It was a dynamic, continuous system. As a heavy stone block was pushed or pulled forward, it would roll over a set of logs placed beneath it. The critical step came when the rearmost log was freed from the weight. Workers would quickly grab that log and run it around to the front, placing it down ahead of the advancing mass. In this way, the load was always rolling forward on a constantly renewing track, a makeshift conveyor belt made of wood. This system converted the high friction of sliding into the much lower friction of rolling, a fundamental mechanical principle they mastered through relentless trial and error. They did not have the equations for friction coefficients, but their empirical understanding was profound. They knew that a lubricated surface or a rolling log could turn an immovable object into a portable one. This practical intelligence, born from close observation of the natural world, allowed them to transform potential back-breaking obstacles into manageable, methodical tasks, one slippery step at a time. Yet all the clever physics of levers and lubricated paths would have been useless without the immense, coordinated power of living muscle. Ancient engineering was a symphony of animal and human effort, a carefully choreographed dance of strength on a truly epic scale. Oxen, with their patient, relentless power, and even elephants, the living cranes of the ancient world, were harnessed to pull the heaviest loads. Their raw strength was not merely applied directly, it was amplified. Through clever arrangements of ropes looped around wooden posts, builders created simple but effective pulley systems. A team of oxen, pulling on a rope that passed over a sturdy wooden fork, could exert a multiplied force, redirecting their power to lift or drag weights that would otherwise be impossible. This was the biological engine that drove the stone across the landscape. But the true marvel was not just the strength of the animals, it was the organization of the people behind them. Moving a single colossal block required the synchronized effort of hundreds, sometimes thousands of workers, all pulling on massive ropes in perfect unison. This was not a chaotic mob, it was an operation run with almost military precision. Foremen or lead pullers would likely have called out rhythmic chants or beats, turning individual exertion into a single, unified force. The social and logistical framework behind these projects was a staggering achievement in its own right. Feeding, housing, and managing a workforce of thousands for decades required administrative skills rivaling those of a modern corporation. There had to be overseers to coordinate the teams, engineers to direct the placement of rollers and levers, and supply chains to deliver food, water, and tools. The pyramids were not just built with stone and rope, they were built with a highly developed social structure capable of organizing human potential on a scale we still find difficult to comprehend. This reveals a profound truth that the greatest ancient constructions were as much a triumph of human cooperation as they were of engineering genius. The mountain was moved not by a single brilliant mind, but by the synchronized will of an entire civilization. Perhaps the most tangible testament to this ancient logistical genius lies on the windswept Salisbury Plain. Stonehenge stands as a monumental riddle, its origins rooted in a journey of staggering ambition. The smaller blue stones that form its inner circle were not local. They were quarried from the Preseli Hills in Wales, a source over 150 miles away. Each of these stones weighs up to 4 tons, and moving them across such a vast and varied landscape without wheels or metal tools represents one of history's most enduring puzzles. The journey itself was likely a masterpiece of mixed media transport. One prevailing theory suggests that after being quarried, the massive stones were carefully loaded onto wooden sledges. Teams of people would have then dragged these sledges down to river systems where the stones were transferred onto rafts. Imagine this slow, deliberate procession, floating along rivers and then navigating the treacherous waters of the Welsh coast and the Bristol Channel, a journey entirely at the mercy of tides and currents. This implies the builders possessed not just strength, but a deep, practical knowledge of maritime geography and seasonal weather patterns. They had to know when the tides would be high enough to carry their heavy rafts and which coastal routes offered the safest passage. Upon reaching a landing point closer to Salisbury Plain, the stones would have been hauled back onto sledges for the final overland trek. This part of the journey would have relied on the very techniques of lubricated paths and log rollers we discussed earlier, with workers painstakingly inching each stone across the rolling countryside. The entire endeavor, from quarry to final placement, speaks of a society capable of extraordinary long-term planning and inter-community cooperation. This was not the project of a single village, but likely a coordinated effort across different groups and territories, a shared undertaking that must have spanned generations. The silent, standing stones of Stonehenge are more than an astronomical calendar. They are a permanent record of human determination and a sophisticated understanding of the land and sea, proving that even in the Neolithic age, our ancestors could orchestrate projects of breathtaking scale and complexity. Far out in the Pacific Ocean, a mystery of human movement stands in silent rows. The Great Moai of Easter Island are more than just massive stone faces. They are monuments to a unique engineering solution born from isolation. Carved from volcanic tuff in a single quarry, hundreds of these statues, some weighing over 80 tons, were then somehow transported for miles across rolling hills to ceremonial platforms along the coast. These people had no large animals to pull the loads, no metal for tools, and no wheels for carts. Their environment offered only wood, stone, and rope, forcing an innovation so clever it almost defies belief. Recent experiments and oral histories point to a method that sounds more like folklore than physics. The statues were made to walk. Teams of workers would use ropes tied around the head and base of a moai, rocking the giant figure from side to side. With each coordinated pull, the statue would pivot on its rounded belly, lurching forward in a controlled, shuffling gait. This was not a simple drag, it was a delicate dance of balance and momentum. The curved base was not an artistic choice, it was a critical engineering feature, acting as a pivot point that allowed the multi-ton figure to be tipped and tilted without crashing to the ground. The rhythm of the pullers was everything. A single misstep could send the monolith tumbling, shattering centuries of work in an instant. This walking method was perfectly adapted to the island's resources and terrain. It required no complex machinery, just strong ropes, coordinated teams, and a profound, intuitive grasp of a statue's center of gravity. The moai did not roll or slide. They ambled across the landscape in a slow, deliberate procession, a testament to a civilization that looked at a stone giant and saw not an immovable object, but a partner in a carefully choreographed dance. This was not a universal technique. It was a brilliant, localized answer to a very specific problem, proving that ancient ingenuity was not a single formula, but a million different solutions waiting to be discovered. The journey of an Egyptian obelisk began deep within the earth, in a quarry of solid red granite. Carving a single 5-story monolith from the living rock was a feat of patience and profound understanding of natural forces. Workers would meticulously drill a series of holes along a predetermined line, not with iron drills but with hard stone pounders. Into these holes they hammered dry wooden wedges. Then came the clever part. They soaked the wedges with water. The wood would swell with tremendous, irresistible force, creating a clean, controlled fracture that separated the perfect obelisk from the bedrock. This was engineering by invitation, coaxing the stone to break itself. Once freed, this 400-ton needle of stone faced its most perilous voyage, a trip down the Nile. The Egyptians timed this operation with the river's annual inundation. They would dig a canal right up to the base of the obelisk, and as the floodwaters rose, they floated a massive, reinforced barge into the canal, positioning it directly beneath the waiting stone. Using levers and the buoyant lift of the water, they carefully lowered the obelisk onto the deck. The river itself became a hydraulic lifting machine, raising the barge and its impossible cargo, ready for the journey to its new home. At the temple site, the real test began. The obelisk now had to be moved from the riverbank to its final standing position. Teams of laborers, likely numbering in the thousands, would drag the stone up a massive, purpose-built ramp of sand and rubble. This ramp was engineered with a crucial feature, a vertical shaft at its summit, directly over the obelisk's intended base. The monolith was painstakingly inched forward until its base was poised directly over this prepared hole. Then, in a moment of breathtaking precision and nerve, workers began to slowly lower the obelisk by letting sand drain out from under the sledge through smaller side channels. It was a controlled descent, a gradual settling until the giant stone slid into its waiting socket, standing upright for the first time. The successful erection of an obelisk was more than a construction milestone. It was a divine statement, a permanent signature of a civilization that had learned to make the very earth and water do its bidding. This mathematical genius was etched into the very ground before a single stone was set. Long before the invention of the theodolite or laser level, ancient engineers turned simple ropes and water into precision instruments. They used knotted cords stretched taut between stakes to measure vast distances with remarkable accuracy. To create a perfect right angle, the essential cornerstone for any square structure, they employed a brilliantly simple trick. They would tie 12 equally spaced knots in a long rope. By staking 3 knots, stretching the rope to 4 knots, and then to 5 knots, they formed a perfect triangle where the angle between the 3-knot and 4-knot sides was exactly 90 degrees. This practical application of what we now call the Pythagorean theorem was not written in a textbook. It was held in their hands, a tangible tool for squaring the foundations of temples and pyramids. Ensuring a perfectly level surface over acres of land was another challenge they solved with elegant simplicity. They dug a network of shallow trenches across the construction site and filled them with water. Because water always finds its own level, the surface of the water in every connected trench would be exactly flat. By measuring down from this consistent waterline to the ground, workers could shave down high spots and fill in low spots until the entire foundation was as level as a still pond. This hydraulic leveling system was so effective that the base of the Great Pyramid of Giza is leveled to within just 2 centimeters, an almost unimaginable feat over such a massive area. This was not guesswork, it was applied geometry of the highest order. They used these principles to calculate the exact slope of a ramp, knowing that a 1% error in angle over a mile-long incline would result in missing their target by dozens of feet. They could determine the volume of a stone block or the amount of earth needed for a ramp, allowing for precise logistical planning. The breathtaking alignment of the pyramids with the cardinal directions, off by less than 1/10 of a degree, speaks to a culture that did not just build, they calculated. They understood that the stability of a mountain of stone relied on the invisible, perfect lines of mathematics laid down first in rope and water. This deep understanding of mathematics was matched by a profound awareness of time itself. Ancient engineers did not fight the seasons, they planned their monumental work around them. The rhythm of the natural world dictated the construction calendar, turning environmental challenges into powerful advantages. Consider the Egyptians and their life-giving river. The annual inundation of the Nile, which flooded the fields for months, would seem like a disaster for any major building project. Yet the Egyptians saw it as an opportunity. This was the very season they chose to transport the heaviest stones. As the floodwaters rose, they channeled this liquid power, digging canals that reached right into the quarries. A colossal obelisk or a pyramid block could be loaded directly onto a barge, floating effortlessly on water that was not there just weeks before. The higher water levels meant their heavily laden boats could navigate channels that were otherwise too shallow, turning a back-breaking overland drag into a smooth, river-borne voyage. The river did not halt their work, it accelerated it. This was not just practical, it was brilliant logistics. The same flood that made farming impossible freed up the agricultural workforce. Thousands of laborers who would normally be tending their fields were available for national construction projects, creating a cyclical, sustainable labor system perfectly synchronized with the environment. Their astronomical knowledge further refined this timing. The precise alignment of structures like the Great Pyramid with the cardinal directions was not a happy accident. It was likely achieved by observing the circumpolar stars, whose points of rising and setting offered a fixed celestial reference far more reliable than the sun. This was engineering guided by the cosmos, the beginning of a new construction phase, or the ceremonial placement of a cornerstone, might have been scheduled for a specific solstice or the heliacal rising of a star like Sirius, which in Egypt heralded the coming flood. This fusion of celestial cycles with terrestrial effort gave their work a dual meaning. It was both a physical achievement and a symbolic act, embedding their architecture into the very fabric of the universe as they understood it. They were not just building structures, they were weaving human ambition into the eternal patterns of the earth and sky. This holistic philosophy, where engineering, astronomy, and seasonal strategy were inseparable, represents a level of sustainable planning that modern society is only now relearning. They understood that the most efficient way to move a mountain was to first listen to the whispers of the river and the stars. The true scale of these projects becomes clear when we consider the human energy required. Behind every stone set into place was a meticulously organized society, a living machine whose fuel was not just food, but shared purpose and remarkable administration. The popular image of countless slaves being whipped into submission is largely a myth. For many ancient civilizations, this work was accomplished through a system known as Corvée labor, a form of national service. Imagine a farmer, his fields dormant during the annual Nile flood. Instead of idleness, he would report for duty at a state construction project, contributing his labor for a set period as a form of tax or civic duty. He was not a slave, but a citizen participating in a grand national endeavor. Alongside him worked skilled artisans, stonemasons, carpenters, and rope makers, whose specialized knowledge was passed down through generations. This was a rotating, seasonal workforce, a brilliant adaptation that utilized human resources without collapsing the agricultural base that fed the entire nation. The social benefits of this system were immense. Working shoulder to shoulder on a project that would outlive them all fostered a powerful sense of shared identity and collective pride. It transformed an abstract concept like kingdom or pharaoh into a tangible collective achievement. This shared labor built more than monuments. It built social cohesion, uniting diverse communities under a single, awe-inspiring goal. The logistical challenge of managing this human engine was itself a monumental feat. Administrators had to house, feed, and supply thousands of people in remote locations for months or even years at a time. Archaeological evidence from the Giza Plateau reveals bakeries capable of producing thousands of loaves of bread daily, vast barracks for workers, and medical facilities treating injuries and illnesses. This was not a chaotic camp, it was a well-run, permanent city dedicated solely to the act of creation. The entire operation required a bureaucracy as sophisticated as the engineering, with scribes tracking every tool, every bundle of rope, and every sack of grain. This social engine, powered by a combination of centralized authority, shared belief, and practical necessity, was the invisible force that turned ambitious blueprints into enduring stone realities. The mountain was moved not by magic, but by the synchronized heartbeat of an entire civilization. That sense of shared purpose, that invisible force driving the social engine, was almost always rooted in something far deeper than civic duty. It was a profound spiritual imperative. For the ancient Egyptians, the act of building a pyramid was not merely constructing a tomb. It was ensuring the very survival of their god-king, and by extension, the stability of the cosmos itself. They believed that upon his death, the pharaoh would journey to join the sun god, and the pyramid was his ramp to the heavens, a machine for resurrection. Every stone they hauled, every perfect angle they aligned, was a sacred act that maintained Mot, the divine order of the universe. Failure was not an option, for a failed pyramid meant a failed pharaoh and a world thrown into chaos. This was not a burden, it was a collective spiritual investment in eternity. Across the ocean, the great civilizations of Mesoamerica were driven by a similar cosmic anxiety. The Maya and the Aztecs built their towering pyramids not as tombs, but as sacred mountains, portals to the realm of the gods. Their entire worldview was based on a fragile cosmic balance that required constant nourishment, often through ritual and sacrifice. Building and maintaining these immense structures was a fundamental part of this sacred contract. The labor itself was an offering, a way to honor the gods who provided rain, sun, and life. Without these temples and the ceremonies performed upon them, they believed the sun might not rise, the rains would cease, and the world would end. Can you imagine the motivation that comes from such a belief? It transforms back-breaking labor into a divine privilege. The mythology was not a separate story told after the fact. It was the blueprint for the entire endeavor. The engineering marvels we still puzzle over today were, for their creators, the physical manifestations of their prayers, the ultimate expression of their devotion and their deepest fears. They moved mountains of stone because they believed the fate of their universe depended on it. But how can we be sure these theories hold weight against the immense reality of stone? The proof often comes not from dusty manuscripts, but from mud, sweat, and modern experiments. A field known as experimental archaeology tackles history's greatest puzzles by trying to rebuild them, using only the tools and materials the ancients had at their disposal. Researchers do not just study the past, they physically reenact it. On Easter Island, teams have successfully made replica Moai walk. They gathered groups of volunteers with strong ropes, tied them to a concrete copy of a statue, and through a rhythmic, coordinated rocking motion, they made the multi-ton figure shuffle forward across the landscape. The experiment was a success, but it revealed something more: the critical importance of the team's rhythm and communication. A single mistimed pull could send the statue crashing, proving that the method was not just about brute force, but about practiced, synchronized skill. Similarly, in Egypt, scientists tested the theory of the lubricated path. They built a massive sledge, loaded it with a heavy stone block, and tried to drag it across dry sand. The resistance was immense, requiring a huge team just to budge it. Then they dampened the sand in front of the sledge. The difference was staggering. The same load now glided forward with remarkable ease, pulled by a fraction of the people. This simple act of adding water transformed an almost impossible task into a manageable one, directly validating the scenes depicted in ancient Egyptian art. These hands-on trials do more than just confirm a method was possible. They often uncover hidden layers of optimization. researchers might discover the ideal water to sand ratio for a slippery path, or the exact number of rope pullers needed to maintain a Moai's balance. They learned through sore muscles and trial and error what the ancients learned through generations of accumulated knowledge. This process bridges a vast gap, transforming historical speculation into a tangible, physical reality. When you see a modern team straining at ropes to walk a statue, you are not just watching an experiment, you are glimpsing the very moment an idea from the past is resurrected and proven true, connecting us directly to the problem-solving minds of our ancestors and finally giving their genius the validation it deserves. This humble, organic material was the bedrock of ancient innovation. Wood was not just a tool, it was a technology in its own right, the ancient equivalent of modern plastic. Its versatility went far beyond the lever and the roller, forming the bones of complex machines that pushed the boundaries of the possible. Engineers constructed towering scaffolds from timber, allowing workers to reach dizzying heights as they dressed the stones of a pyramid. They built wooden cranes, intricate arrangements of beams and ropes that functioned as powerful hoists. Some cultures even carved primitive gears from dense hardwood, creating the first mechanical calculators or water-lifting devices. This was not simple carpentry, it was mechanical engineering in its most fundamental form. The true mastery lay in their intimate knowledge of the material itself. They did not see a simple log, they read the wood grain like a map of its inherent strength. For a lever that would bear immense, constant pressure, they selected a dense hardwood like oak or ash, prized for its resistance to splintering. For the axle of a sledge or a component that needed to withstand sudden jolts, they might choose a more flexible wood like elm, which could absorb shock without fracturing. This material science extended brilliantly to the water. To build a vessel strong enough to carry a 70-ton stone obelisk, shipwrights relied on sophisticated wooden joinery. They fashioned strong, watertight hulls using interlocking joints secured with wooden pegs known as tree nails. These swelled when wet, locking the entire structure together into a single, immensely resilient unit. The proof of their skill survives in the most unlikely places. In the arid tombs of Egypt or the oxygen-depleted mud of northern European bogs, archaeologists have uncovered wooden tools and structural pieces that remain intact after thousands of years. Their preservation is not just a lucky accident of climate, it is a direct result of the ancient artisans' understanding of how to select, season, and work their material to resist decay. The great stone monuments that dominate our imagination simply could not exist without this foundational and often overlooked mastery of woodcraft. The true challenge began not with moving the stone, but with convincing the mountain to let it go. Before a single block could be coaxed across the desert, it had to be surgically separated from the living earth, a process demanding as much finesse as force. Ancient quarries were open-air laboratories of applied physics, where engineers manipulated the most fundamental forces to solve the first great puzzle, extraction. One of their most dramatic methods was fire setting. Workers would build intense, controlled fires directly against the granite or limestone face. As the rock glowed with heat, they would suddenly douse the flames with water or vinegar. This rapid cooling created a violent thermal shock, the stone expanding and contracting so quickly that it fractured along natural fault lines. It was a form of geological persuasion, using heat and cold to convince the unyielding rock to break. But brute force was only part of the story. For a cleaner, more precise cut, they turned to the quiet power of wood and water. They would meticulously drill or chisel a line of holes along the desired fracture path. Into these holes they hammered dry, seasoned wooden wedges. Then they soaked the wedges. As the wood absorbed the water, it swelled with an irresistible, silent pressure. a force so immense it could cleave a 100-ton block from the bedrock along a perfectly straight line. This was not a chaotic smash and grab. The evidence left behind in ancient quarries is astonishing. Rows of partially extracted blocks still sitting in their beds, their sides showing the precise tool marks and fracture lines where work was halted. This reveals a profound, intuitive grasp of fracture mechanics. They knew exactly how to place their wedges to guide the break, understanding the stone's internal grain and stress points. The quarry was not merely a source of raw material. It was the first and most critical stage of construction, where the raw, chaotic power of the earth was patiently and skillfully won over, one perfectly shaped block at a time. The quarry was only the beginning. Once a multi-ton block was finally freed from the earth, its most grueling journey commenced, a slow, grinding trek across the open land. For this, the ancient engineer's most vital tool was the sledge, a massive wooden platform that transformed an unwieldy stone into a portable load. These were not simple sleds, but robust frameworks of heavy timber, carefully constructed to distribute the immense weight and prevent the stone from cracking under its own pressure. But the true challenge was not the sledge itself. It was the immense friction between the wooden runners and the ground. A direct pull across dry earth would have been impossible, requiring a force greater than any team of men or oxen could muster. The solution was to change the very nature of the ground itself. In Egypt, workers prepared the path by pouring water onto the sand or clay ahead of the advancing sledge, creating a slick, hard surface of mud that dramatically reduced resistance. This was not a simple trick. It was a carefully calibrated process, using just enough water to create a lubricating film without turning the path into a bottomless mire. In other parts of the world, they laid down a different kind of track, a continuous road of wooden rollers placed perpendicular to the direction of travel. As the sledge inched forward, teams of workers would constantly retrieve the rollers from the back and rush them to the front, creating a makeshift, endlessly renewing conveyor belt. The grinding, squeaking progress of a multi-ton block on these rolling logs must have been a symphony of controlled effort, a testament to relentless, coordinated labor. In some places, like the mysterious parallel grooves known as cart ruts on Malta, we see what might be the remains of more permanent solutions, stone pathways worn down over centuries by the repeated passage of heavy sledges. These prepared roadways, with their hard, smooth surface, would have been the ancient equivalent of a modern heavy-haul highway, a dedicated infrastructure project just for moving stone. This overland phase was the ultimate test of endurance and logistics, a marathon of muscle and will where progress was measured in feet per day, where the sheer organizational capacity of a civilization was stretched to its absolute limit, all to bring a mountain, one agonizing step at a time, to its final, impossible home. The relative ease of a water journey was an almost magical transformation for these ancient builders. A stone that would have required 1,000 straining laborers to drag for weeks overland could be set afloat on a single, carefully built vessel, its immense weight suddenly rendered weightless by the supportive embrace of the water. This principle of buoyancy turned rivers and seas from barriers into the most efficient highways the ancient world would ever know. To harness this power, they became master shipwrights, constructing colossal rafts and barges from the materials at hand. In Egypt, they built robust, flat-bottomed barges from acacia wood, lashing the timbers together with powerful ropes made from papyrus. These were not delicate boats, they were floating platforms engineered for one purpose, to carry an impossible load just once down the Nile. A single barge, documented in reliefs, was described as being over 100 feet long, a veritable fortress of timber designed to carry a 200-ton obelisk. The process of loading was itself a feat of engineering. They would dig a canal next to the quarried stone, float the barge in, and then, using a system of levers and counterweights, or simply by waiting for the annual flood to raise the water level, they would carefully maneuver the monolith onto the deck, securing it for its voyage. Once laden, the vessel became a sluggish behemoth, nearly impossible to steer with oars or sails alone. The solution was a coordinated towing operation. Teams of smaller, agile rowboats would take up positions ahead, their crews pulling on massive tow ropes, while on the riverbanks, lines of men would act as a human tugboat, heaving the rope over their shoulders and walking the barge down river in a slow, synchronized march. This was logistics on a grand scale, a moving spectacle of human and hydraulic power working in perfect concert. The choice of timing was everything. By scheduling these transports for the peak of the Nile's inundation, the engineers gained a double advantage. The higher water levels not only made loading easier by bringing the river to the stone, but they also submerged sandbars and obstacles, creating a deeper, clearer channel for their precious, ponderous cargo. This was not just using a river, it was a collaboration with its entire seasonal cycle, a perfect fusion of human intention with the predictable rhythms of the natural world. That perfect seam between two stones, one that even a razor blade cannot penetrate, is the signature of a master craftsperson. Across the world, from the mountaintop walls of Machu Picchu to the sprawling foundations of the Giza pyramids, we find these impossible joints, stones cut with such astonishing precision that they lock together without any mortar at all. This was not magic, but a technique of immense patience and skill known as drafting. The process began with the rough shaping of a stone block, but instead of trying to make it perfectly flat on all sides, the masons would focus on the edges, creating a perfectly smooth, narrow margin around the block's perimeter. This finely dressed border or draft was the key. The center of the stone face could be left slightly recessed, saving countless hours of labor while still ensuring that the most critical part, the meeting line between two blocks, was flawless. To achieve this seamless fit, the stones themselves became the final measuring tool. After the initial drafting, masons would use harder stone pounders to painstakingly grind the surfaces together. They might place a layer of abrasive sand between the blocks and then swing the stones back and forth, or slide them against each other in a slow, grinding dance. With each movement, the high spots on the stones would be worn down while the low spots remained untouched. This continued for hours, perhaps days, until the two surfaces mirrored each other so perfectly that they met across their entire area, creating a bond of incredible strength. This interlocking construction was far more than an aesthetic choice. It was a brilliant feat of seismic engineering. In an earthquake, a rigid wall held together with brittle mortar can crack and collapse. But a wall built with these drafted, interlocking stones is flexible. When the ground shakes, the individual blocks can shift and sway minutely, absorbing and dissipating the energy. Once the tremor passes, gravity simply pulls them back into their original, perfectly locked position. The sheer amount of time and effort this process required speaks volumes about the values of these cultures. They were not building for a decade or a generation, they were building for eternity. Every perfectly fitted seam was a statement, a declaration that their work would defy time itself, standing as a permanent testament to human patience and the relentless pursuit of perfection. Some of the most captivating theories about ancient construction move beyond the physical into the realm of the unseen, into the power of sound itself. Could sonic vibrations have been a tool to move mountains? This is the acoustic hypothesis, a speculative idea that suggests certain resonant frequencies might have been used to make massive stones lighter or easier to manipulate. While we have no definitive proof like an ancient sonic drill, some researchers point to persistent legends and curious artwork from various cultures. Tibetan monks, for instance, speak of legends where chanting and the deep, resonant thrum of trumpets and drums helped lift blocks into place. In some ancient Egyptian and Mesoamerican iconography, there are depictions of figures holding what appear to be musical instruments near construction sites, which some interpret as a hint at sonic rituals. The scientific principle at play here is resonance, the idea that every object has a natural vibrational frequency. If you match that frequency with a sound wave, you can cause the object to vibrate intensely. In theory, a powerful, precisely tuned sound could create a standing wave that might counteract gravity, or at the very least, reduce the friction between a stone block and the ground, making it feel almost weightless for those pulling it. Imagine the profound coordination this would require, not just of muscle, but of voice and instrument, creating a unified sonic force. Of course, this remains a highly controversial and unproven theory, sitting at the very edge of historical archaeology. But its enduring appeal lies in what it represents. It forces us to consider that ancient knowledge might have extended into areas of physics we are only now beginning to understand, realms where sound was not just for communication or ceremony, but a tangible, physical power. Whether true or not, the acoustic hypothesis expands our sense of possibility, reminding us that the full scope of their genius may still be echoing just beyond our hearing. This profound resourcefulness was never a rigid formula. Ancient engineers were masters of adaptation, constantly reading the landscape and tailoring their methods to its unique personality. They did not try to conquer the terrain, they collaborated with it. In rugged, mountainous regions where lifting a stone up a cliff face would be a nightmare, they used gravity as their primary engine. They would carefully lower massive blocks on controlled descents, using a system of ropes and anchor points to turn a deadly fall into a slow, deliberate procession downhill. This was engineering in reverse, a clever inversion of the usual challenge. Meanwhile, in vast desert areas, they saw the hard, flat surfaces not as barren wastelands, but as perfect, naturally occurring highways for their heavy sledges. The very environment that seemed so hostile became their greatest asset. This deep environmental intelligence extended to the very bones of the earth. They understood local geology intimately, knowing which rock types were easiest to quarry and work. They might choose a softer sandstone for the core of a structure, reserving the harder, more difficult granite for the outer casing or ceremonial elements. This was a pragmatic approach, a form of material efficiency that saved immeasurable time and effort. The principle is clear: there was no single right way to move a mountain. Instead, there were countless ways, each one a bespoke solution, perfectly tailored to its specific context. A technique that worked flawlessly on the hard-packed clay of Egypt would be useless in the swampy deltas of Southeast Asia, and vice versa. This context-specific design is perhaps one of the most powerful lessons from the past. It emphasizes that true ingenuity lies not in imposing a one-size-fits-all solution, but in observing, listening, and ultimately working in harmony with the local conditions you are given. It is a reminder that the most sustainable and brilliant engineering often looks less like a master plan and more like a thoughtful conversation with the world. The same elegant solutions appear across the globe, separated by oceans and centuries. How did cultures from the Egyptian desert to the Mesoamerican jungle all arrive at the use of ramps, levers, and lubricated paths? This is the great puzzle of parallel invention. Direct contact between the pyramid builders of Egypt and the temple architects of Cambodia was virtually impossible, yet both understood that a long, gentle slope was the key to lifting immense weight. The answer lies partly in the universal language of physics. The laws of leverage, friction, and buoyancy are constants, written into the fabric of reality. Any society with brilliant, observant minds, when confronted with the challenge of moving a mountain, would inevitably experiment with a log placed under a heavy object, or notice how a wet path eases a sledge journey. These are not secrets to be hoarded, but discoveries waiting to be made by anyone who truly looks at the world. Yet the spread of more specific, refined techniques hints at a different kind of movement, the movement of people. Along the sprawling trade routes of the ancient world, like the Silk Road, caravans carried more than just silk and spices. They carried ideas. A skilled stonemason from one kingdom, traveling to another for work, could bring with him the precise knowledge of how to draft a stone for a perfect, mortar-less fit. This subtle diffusion of expertise meant that a clever innovation in one region could, over generations, ripple outward, adapted and refined by new hands. So the global story of ancient engineering is a dance between two powerful forces, the inevitable discovery of universal principles and the slow, deliberate sharing of hard-won craft. Human ingenuity, when faced with the same monumental obstacles, consistently converges on the same brilliant, elegant answers, proving that the drive to build is a universal thread connecting all of humanity. These breathtaking monuments cast long shadows of sacrifice. The sheer volume of resources consumed was staggering, a constant drain on the entire economic system. Entire forests were felled to produce the timber for sledges, scaffolding, and the colossal ramps that snaked up the sides of pyramids. Quarries operated ceaselessly, scouring the landscape to feed the insatiable appetite for stone. But the most significant resource of all was human energy. Feeding, housing, and managing a workforce of thousands for decades required a logistical machine of its own. A significant portion of the kingdom's agricultural surplus, the very foundation of its wealth, was redirected from the general population to sustain the workers on the state project. This was not a side endeavor, it was a central, all-consuming national priority that mobilized a huge fraction of the society's total economic output. The true cost was measured not just in stone, but in the relentless effort of generations. On Easter Island, this equation may have reached a tragic breaking point. The very act of creating the iconic Moai, of felling the giant palm trees for rollers and ropes, is theorized to have led to catastrophic deforestation. Without trees to anchor the soil, the land eroded. Without timber for canoes, the islanders lost their ability to fish in deeper waters. The society that had poured its heart and soul into carving giants may have ultimately been crippled by the very process that defined its glory. This raises a haunting question for our own time. Where is the line between ambitious creation and unsustainable consumption? These ancient wonders stand as a dual legacy, magnificent proof of what we can achieve, but also silent warnings of the potential price. They challenge us to consider the long-term consequences of our own grandest projects, reminding us that even the most glorious achievements are built upon a foundation of real-world costs. These ancient principles are making a quiet comeback in our modern world. The same low-tech, high-skill approach that moved mountains without iron is now inspiring a revolution in sustainable design. Today's green architects and engineers are looking back to these methods, not for nostalgia but for solutions. They see the profound intelligence in a system that used renewable materials, minimized energy consumption, and produced almost zero waste. The ancient reliance on gravity for transport, on water for lubrication and power, and on passive solar alignment for climate control are no longer forgotten arts. They are being reimagined as core tenets of a new, more responsible way of building. Imagine a modern structure designed to use natural ventilation instead of energy-hungry air conditioning, or a water system that uses gravity flow rather than electric pumps. This is not a step backward, it is a step toward wisdom. The ancient focus on durability stands in stark contrast to our disposable culture. They built for millennia using materials and techniques that ensured their work would endure. Our modern constructions, often designed with planned obsolescence, rarely last a century without major renovation. The ancient world understood that the most sustainable building is one that never needs to be replaced. By studying how they moved mountains, we are not just uncovering lost secrets, we are rediscovering a fundamental philosophy. It is a philosophy of working in synergy with natural forces, not overpowering them with brute technological force. It respects material limits and harnesses environmental opportunities. In an age of climate crisis and resource depletion, these time-tested lessons offer a path forward that is both brilliantly innovative and deeply ancient, proving that the most advanced engineering might just be the one that leaves the lightest footprint. Even with all our discoveries, the past holds its secrets tightly. The massive lintel stones at Stonehenge, perched high atop their uprights, present a puzzle that still fuels intense debate. How did a society without cranes lift these multi-ton capstones into perfect position? Some theories suggest the construction of enormous timber platforms and ramps, using levers and ropes to inch the stones upward. Others propose a more dramatic method, that they might have built a wooden framework and packed it with earth and rubble, creating a temporary hill that workers could climb to simply push the lintels into place before dismantling the entire structure. We simply do not know for certain. Across the sea, the Great Pyramid of Giza presents another great unknown. While ramps are the accepted solution, their exact design remains one of archaeology's greatest riddles. Was it a single, straight ramp stretching far into the desert, a spiraling ramp corkscrewing up the pyramid's faces, or a complex system of internal ramps hidden within the monument itself? Each theory has its merits and its flaws, and until definitive evidence is found, the question remains open. These gaps in our knowledge lead to a tantalizing possibility. Could there have been brilliant, yet simple, techniques that relied on materials which have long since returned to the earth? Perhaps they used intricate networks of ropes made from perishable fibers, or temporary structures of wood that left no trace after millennia. The field of archaeoengineering is alive with these questions. It is not a static science of dusty facts, but a dynamic detective story where a new radar scan of the plateau or a fresh analysis of tool marks in a quarry can overturn decades of accepted wisdom. These ongoing debates do more than just puzzle us. They connect us to the enduring mystery of human achievement. They remind us that history is not a closed book but a vibrant, continuing conversation. And every new discovery has the power to reshape our understanding of what our ancestors were truly capable of. Those silent, weathered stones still standing after millennia are the ultimate proof. The achievements of ancient engineers are far more than historical footnotes. They are a breathtaking exhibition of human potential in its purest form. Their success was not born of magic or alien intervention, but of a deep and profound conversation with the world around them. They listened to the physics of a lever, understood the strength of a twisted fiber rope, and learned to read the seasons and the stars as their construction calendar. This intimate knowledge, combined with a social engine capable of uniting thousands toward a single goal, allowed them to overcome what we would see as insurmountable limitations. They did not have iron, so they perfected the art of stone. They did not have wheels, so they mastered the slide and the roll. Every apparent constraint became a catalyst for a more elegant, more sustainable solution. From the lubricated paths of Egypt to the walking statues of Easter Island, their ingenuity whispers a powerful lesson to our modern world, a world grappling with its own mountains of challenges. As we face issues of resource depletion and environmental change, their legacy is a compass. It points toward a philosophy of working with nature, not against it, of valuing durability over disposability, and of recognizing that our greatest strength has always lain in collaboration and shared purpose. Let those ancient stones be more than a monument to the past. Let them be a call to action for our future. They urge us to harness our own collective ingenuity, to build not just for today, but for the thousands of years to come. We would love to hear which of these ancient mysteries you find most inspiring. Share your thoughts in the comments below. And if you want to continue exploring the wonders of our shared past, be sure to subscribe.